Welcome everyone to our video on net ionic equations. In this video, we are going to look at the conceptual basis for why we write net ionic equations. And then we're going to go through an example where we take a balanced chemical equation, we write the total ionic equation, we identify spectator ions, and we write the net ionic equation. Before getting into the mechanics of writing net ionic equations, let's recall two important points. First, remember that when we have ionic compounds which are dissolved in water, or they're aqueous, they have dissociated into their individual ions. So they don't actually exist as the compound that's held together anymore. They exist as individual ions in the water. So even though we will often write an equation where we write it as the compound together, NaCl aqueous, that's not actually how that ionic compound exists in reality. In reality, they are individual sodium 1 plus and chloride 1 minus ions that are held in solution by the water molecules. When we've looked at chemical equations so far, those chemical equations are often referred to as molecular equations. Since so much of chemistry goes on in aqueous solutions, it's often more convenient to write these equations as ionic equations. And these are equations where the aqueous ionic compounds are written as individual ions rather than the compound as a whole. Our endpoint in this lesson will be a net ionic equation, and a net ionic equation only shows the ions and other chemical species which are involved in a chemical change, and we omit any chemical substance which may be present in the reaction but not actually involved in the chemical change. To do this, let's go over to the whiteboard and do an example where we take this molecular equation for a double displacement reaction and write it as a net ionic equation. Our first step in finding the net ionic equation is to balance the molecular equation. So let's do that now. Our second step is to take all of the ionic compounds which are dissolved in water or that are aqueous and rewrite them as ions. My first compound here is sodium chloride. There are two sodium chlorides, so that means I have two sodium ions and two chloride ions. Note that the coefficient remains out front for the ions, and I've included the charges as well. Let's continue this for the rest of the aqueous compounds. My second line here in green is the total ionic equation. A total ionic equation is an accurate representation of how each of these chemical substances actually exists as reactants and as products. Aqueous ionic compounds are written as ions, which, as we've learned, is how they exist in solution. The only substance which remains quote-unquote together is our final product, which is that precipitate, lead chloride. Now, if you look at the reactants and products here, you will see some ions which are the same on both the reactant side and product side. So for example, we have two sodium 1 plus ions in solution on the reactant side, and 2 sodium 1 plus ions in solution on the product side. So there has been no change to the sodium ions. We have some sodium ions dissolved in water beforehand, and we have the same quantity with no change in charge afterwards. Since the sodiums have not undergone a chemical change, we refer to them as spectator ions. Spectators, as in they're present for the chemical reaction, but they are not involved in the chemical reaction. My next steps is to identify all of the spectator ions, and we will cross them out when they appear in the same quantity, charge, and state on both the reactant and product sides. My next step will be to rewrite the equation. And my final line here is the net ionic equation. A net ionic equation only shows the chemical species which are involved in a chemical change. In this case, we have chloride and lead 2 plus ions combining to form a precipitate. In your final answer, your charges on the reactant side and product side should equal. So the charges should balance, and of course, the chemicals should balance as well. So let's check 2 chlorines on the product side, 2 chlorines. On the reactant side, 1 lead. On the product side, 1 lead. If I look at my charges, we have 2 times 1 minus from the chlorines, and then 1 times 2 plus from the lead. So there's no net charge on the reactant side. And of course, we have an ionic compound which has no net charge on the product side. If either the chemical species or charges do not balance, it means you've made a mistake in either balancing the original equation or separating them out into ions. Let's review the steps that we went through. First, which we didn't go through together, but we've learned already, we use the solubility rules to determine which compounds will be aqueous and which will be solids, or for that matter, liquids or gases. Our next step was to balance the molecular equation. The third step was to take all of the ionic compounds which are aqueous and rewrite them as ions. So we split them apart and wrote them as ions. This was referred to as the ionic equation or the total ionic equation. Once we had separated all of the ions, we identified the spectator ions, which recall is any substance which appear in the same quantity, the same state, and the same charge on both the reactant side and the product sides of the equation. Once we identified those, we crossed them out, and we did that in recognition that since they are not involved in the chemical change, we can take them out of the chemical equation. And finally, we rewrote the equation only showing the substances which were actually involved in the change. And this is referred to as the net ionic equation.